All right, so pin 1 is ground. If you look at your picture, you'll also see pin 8. I know pin 4 also is connected to VCC, but pin 8 is VCC. And what is VCC?
Power.
Power. You are correct. And that, for us, is 5 volts. DC, and it has to be on a regulated circuit, okay? For those of you in my class, you cannot put it on a voltage divider because it will consume more or less current over time, and it will change the voltage input if it's on a divider, okay? So, all right, so pin 1 is ground, pin 8 is power. Now, let's talk about the output. Pin 3. Pin 3, pin 3 produces the square wave. Okay? And it will produce a square wave of 0 to 5 volts. And remember I talked about inverters and how they would drive 6 other devices? This will too. It acts just like inverters, okay? Drives 6 other devices. All right. Pin 4, which is, let's see, where is it? Right here. Pin 4 is a reset, and for the most part, unless we're driving it with other TTL circuitry, we can tie that high. Okay, now there are cases where I want to trigger it. I might want to get it in sync with something else that I'm doing. So I can reset it with pin 4 so it'll sync up. Okay, so I might be looking at some kind of wave here that's doing its thing, and I want that to start right here, then I can use pin 4 to get that done. I can drive it with an inverter or something, and I can pulse it, and it will start, it will trigger on whatever my signal is. This is my signal. It will trigger right there and start so I can utilize my pulses, and they won't be out of whack, okay? They won't be out of faster or slower, okay? Does that make sense, Steve? Okay, all right, so pin 4, we're going to tie pin 4 high. So we're just going to take it over here and tie it right there, okay? All right, because we don't really want to use it at this point in time. Now, 2 and 6. 2 and 6 are threshold and trigger. In this particular case, they have to be connected together. And in most cases, they will be to get it to oscillate. Okay? I have not had to utilize those separately, but there are some cases where you could actually utilize them separately to set the threshold up or down. 2 and 6 need to be connected together. So this is 2 right here, and this is 6. So what I do is I just simply jumper those 2 together like this. Okay? And that takes care of those 2 pins. They're out of my way. Oh, 7. All right. 5. Notice 5 doesn't show up. 5. We look at 5, we see that it's a control lead. And for those of you who are in my class, notice there's a little voltage divider in here. Notice from VCC to ground, this is where you use a voltage divider. What do we know about the inputs of op amps? Well, we haven't studied them yet, but they are high impedance. So we can use a voltage divider because there's very, very little current flow. So the resistors will not change. They're built in, by the way. They won't change. So notice the control right here is just hanging out there, and that's okay. We can just leave it hanging out there because the voltage divider has already set the voltage. Now we can change that up or down linearly and change the control, which will set this so it will do other things, okay? In other words, we can generate other sawtooths and things like that, okay? We're not going to. We're just going to leave it the way it is because that voltage divider right there, those three resistors, will keep it in sync. It'll keep it so it's oscillating a square wave, okay? Make sense? Another example of where voltage dividers operate well, okay? All right, so we're not going to worry about pin 5. So I always just put an X there. Don't tie it high, don't tie it low. Just leave it sit. Okay? If you tie it high or tie it low, because I know sometimes it's like, oh, I got to put every pin somewhere. People kind of get into that mindset. They all got to be tied something. And in a lot of cases, that's really important. In this case, don't tie it to anything or it's going to mess up your output, okay? It's one of those things where just ignore it, okay? It'll do its thing all by itself. All right, so what does that leave? Well, it leaves 6, 7, well, 6 and 2 are connected together, but 6 and 7 and 2 are part of this network. Now this almost looks like a divider network, and it would fool you, except for it isn't. This resistor right here is connected to B plus here, 5 volts. Okay? Usually you can get away with a 1 to 10 k ohm resistor there. What does it do? It charges this RC network here. This is an RC network. We haven't studied RCs. We'll study them tomorrow, but we've studied RLs. And what do we know about RL networks? We know that an RL network charges up over a time period, right? One period, 63%. It's almost charged up. We consider it pretty much charged up in one period, okay? But that's how far it gets, all right? An RC time constant is the same. It's a resistor and a capacitor, and it charges up over a time period of 63%. We need this to charge up so that it will delay that long. See this waveform here? Charges up. And as soon as it gets to that point, the control circuitry in here will short that out, and it'll start the discharge. It actually shorts it out up here, okay? See here, the transistor right here, we haven't studied that, but we have a discharge in there. And that shorts out this RC, and then the capacitor starts to discharge through the resistor, and it goes back down. See how it goes? Up, down, up, down. That causes this little flip-flop to flip back and forth. Boom, boom, boom. I cannot get a square wave out of this by itself. I can't take a capacitor and a resistor and hook them up. Let's see here if I can do this. So if I took a resistor like this and I put a capacitor here and I hooked it up to a switch like this, and I hooked it up to say 12 volts, when I closed the switch, if I looked at the voltage occurring across this resistor R1, let's say I looked at the voltage, I would see a charge up, and then when I opened the switch, I'd see the capacitor discharge, right? Because the resistors from the negative to the positive, what's going to happen? those electrons are going to try to escape back off that plate, back through that resistor, so that that capacitor becomes neutral, right? Capacitors are just plates with a dielectric in between. All of you know a little bit about capacitors, right? Anybody doesn't? Raise your hand if you don't. Okay, let's talk about a capacitor. A capacitor, two plates with a dielectric in between, like an insulator. A lot of capacitors use wax paper, or did. Now they're more ceramic-y, but used to be wax paper all the time. Just rolled them up. Some of them were electrolytic, so they had a little chemical in there so that they could store more electrons. What happens is we have a plus plate and a minus plate, and when we charge the capacitor up, we just put all the electrons here. And what does that do over on the other side? Well, it is deficient on this side of electrons, so it makes it positive. Okay? So how do I do that? Well, I just take a power supply and I put it across the leads right here. Let's say I do 12 volt. So I put the plus here and I put the minus here. And what happens to all electrons? Well, power supply is trying to pump the electrons around to the plus side, right? If I put the capacitor in there, all electrons pile up on the negative side of the plate. All the pluses are from all the electrons being sucked out of the positive side, because it's just like a pump, okay? And it charges that capacitor up. Now, I know that every one of you in physics class or somewhere has seen a capacitor and somebody charged up, about this big around, you know, really big, and then they took a wire and they went whap, and it burned off the end of the wire, didn't it? Y'all seen that? No? Maybe? Possibly? No? Okay. Don't do it to a supercapacitor though. That'll just tear things up something fierce. I got a great big one out in the car, in fact. Yeah. No, I think we'll stick with I got some littler ones back there. Tiny ones don't see much of a spark. If they get big with terminals on them, you can see a pretty good spark. It's kind of fun to do when we really get into capacitors. We'll do that in my beginning class. But the idea is that the electrons can't get across the insulator. Glass, wax paper, all kinds of different things are used, okay? In our case, we want them to charge up, and then we want to have a resistor. Notice this resistor is in parallel with the capacitor. So the power supply will charge the capacitor. It also will allow some current to run through the resistor. So we don't really want to use like a 1 or 10 ohm resistor, because right away our power supply is pumping a lot of current through that resistor. But if we use something in the 10K range, a small amount of current will pass across that resistor. But the idea is that we can charge up the plates on this capacitor, and when we open the switch, they will discharge through the resistor. And we end up with this. Charge up, discharge. Charge up, discharge. Notice we have a capacitor resistor network here. Okay? You say, well, what's this? This is the resistor that actually charges that up. So it's really simple. What they did was they just said, okay, fine. If you want to be hard about it, what we'll do is we'll give it a limit resistor like this, and we'll let that charge R2. We'll let that charge up this network right here. And then we'll let this one discharge it. Okay? So we good with that? When we close the switch, it just charges through that resistor. When we open it, this just goes away, doesn't it? Because it's open. So now we just have that little circuit right there. Okay? So what it does is it creates this waveform. And now you can visualize, yeah, that's the waveform it would create, wouldn't it? Charge up, discharge. Now to be a little more sawtoothy over here, if we closed and opened the circuit, you know, because it up down. Actually, though, it wouldn't, would it? Because the capacitor,
discharges at a certain rate.
yeah, what's the capacitor look like on the graph? Goes up one time period, 63%. So it charges really quickly because there's no electrons in this capacitor. So they're just piling in there. But once it starts to get full, what happens? Then it tapers off. And it keeps tapering off and tapering off. And if we didn't use any calculus, we'd never be able to figure out where it actually ended up, fully charged. So you have to use a little calculus to look at the curve. So what they said is, okay, enough is enough. We don't want to wait around here 6 months for it to get all fully charged up. So we'll just say one time period is 1t, and that's 63%. So if it takes 5 minutes, okay, one time period, 63%. If it takes 1 second, that's the time period. You can calculate that. We won't do it today, but that's what happens, okay? So we're just trying to get something where everybody can agree, and we don't have to wait around unless we really want to. We don't have to wait around to get it charged up all the way, okay? All right, so here's our charge up. Boom, 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 boom. And you can see that it's starting to curve a little, huh? But it never gets all the way up where it gets flat, because what happens? The circuitry in here says, okay, I'm done. And it shorts it out right here with this transistor to ground, shorts that out. Now, if we didn't have that resistor in there, what would it do to the supply? It shorts the supply out. So the reason that resistor's in there for here, because it doesn't really matter here, does it? I mean, we could use it just right from the supply, couldn't we? The reason it's in here is because this transistor turns on. Notice when it flops over, it's on one of the outputs, okay? So these outputs flip-flop back and forth, right? A flip-flop like this one has a Q and a Q not. It has a set and a reset. Now you will study these. I'm not sure how long. It'll be a while yet, I think, before Carol gets to those. But you will study these. They're called a flip-flop. And they do exactly what they sound like. That's why they call them flip-flops. And what happens is the outputs go back and forth. If this is a 0, this is a 1. If this is a 1, this is a 0. So you take a look here. Notice that the base of this transistor, so we're just going to look at that transistor just like a relay, okay? In Bill's class, you've studied relays. It's just like the points on a relay. This output right here closes them, opens them, closes them, opens them. When they close right here to ground, it shorts that out. That resistor, excuse me, that resistor limits the current from the power supply, because if we didn't have that resistor in, it would short out the ground, and that would cause power supply to go to ground and it blow a fuse. So we have to have a big enough resistor there so that it doesn't blow the power supply, okay? When it does that, it does this. It shorts out. Notice it's pretty straight, but notice it doesn't get all the way down. And watch what it's going to do here. See, it's starting to curve right there. You see it just started to curve, just started to curve. When it hits that point, what happens is the flip-flop flips back over, turns the relay off, output changes, and guess what? This resistor charges up this capacitor resistor network, and boom, we're on our way again. And that's all it does. Just sits and does that all day long, depending on what components you put in there. Make sense? All right. So now we know, but we have to know how to hook it up. Well, if we look at this, we go, oh, let's see. 2 and 6 are connected together. We've already got that. We need an RB between 6 and 7. So we're going to place a resistor between 6 and 7. We'll call it RB, just like they did. Oh, and we need a charge resistor, RA, to B+. And it comes off of which one? 7. So we just go right up here. Oh, we don't even have to go past that, do we? We can just go like this and hook right there. This will be RA. RA will charge. Oh, we didn't put in the capacitor, did we? Not going anywhere if you don't put a capacitor in. Okay? So where does our capacitor go? It goes right here. By the way, this designates an electrolytic capacitor, which means this side is plus and this is minus, and that's correct because the minus is on ground. We don't have to use an electrolytic. We can just use a standard ceramic capacitor with no polarity, okay?